In section 3.5, we're going to look at implicit differentiation. Up to this point, most of the functions that we have encountered have been expressed in what's referred to as explicit form. In explicit form, we have the dependent variable by itself, and it's going to have an expression of the form either y equals stuff that only involves x, or it could be of the form, f of x equals 3x squared minus 5. In this section, we will tend to use the y equals notation as opposed to the f of x notation. So that's what we mean to have a function that's defined explicitly. We have y equals stuff that only involves the x variable and constants. The equation x times y equals to 1 does not have the y by itself, and so we would consider this equation to be implicitly defined. So the equation x times y implicitly defines y as a function of x. So at the end of the day, we're still thinking of y depending upon x. So we still think of y is equal to f of x, or y having an x dependence. Sometimes it's possible to take an equation and solve it for y, like we have here. You divide both sides by x, and then you would have y equals 1 over x. This form of the equation was the implicit form, and we were actually able to explicitly solve and get the y by itself. It's not always possible, however, to take a implicitly defined function and get the y by itself to write it in explicit form. Nonetheless, we can still find derivatives and things of that matter by using implicit differentiation. To give an illustration of this, let's take a look at the following. If we had d dx, so let's take the derivative with respect to x of x squared. We know that rule would say you do 2 times x, bring the power down. That was our general power rule. And we saw what it would look like from the chain rule. So let's suppose I had u, where u is some function of x. And in this case, we're going to say y. So what would be the derivative of y squared with respect to x? Well, again, if you kind of cover it up for a moment, the outer function is the squaring function, and the inner function would be like the function y, which is y of x. To do the derivative, we would apply our basic rule to do the derivative of 2 to a power. If something to a power, you just bring the power down, keep the y the same, reduce the power by 1. But now what's going to happen is from the chain rule, we need to multiply by the derivative of the inside thing. Well, what is the derivative of y with respect to x? That is dy dx. So this is going to be 2y dy dx. Or if we use the y prime notation, we could call it 2y y prime. So some students will kind of reduce this to the fact of if you compare these two that we just did. The derivative of x squared is simply 2x. The derivative of y squared is 2y, but then don't forget to tack on the y prime. So on one hand, the moral of the story is anytime you do the derivative of something that involves a y term, apply the rules as you're used to, but then don't forget to multiply that because of the chain rule by dy dx, and then this allows us to take the derivatives of implicitly defined functions. For instance, we just saw this a moment ago. The derivative with respect to x of x cubed, that's a basic power rule. We bring the power down and reduce the power by 1. We know that the derivative of x cubed is 3x squared. If we now want to take the derivative with respect to x of y cubed, again, it's going to be a power rule. We bring the power down, reduce the power by 1, and then from the chain rule, we need to multiply by the derivative of the inside, and I'll call that dy dx. Okay, if you want to use the prime notation, it's the same thing. You could have even written your answer as 3y squared times y prime. Let's take a look at part C. We want to take the derivative of this expression, which has 2 terms. Our rules for differentiation say we can differentiate term by term. The derivative of x is 1. The derivative of 3y, well, that's going to be 3, but then from the chain rule, we need to multiply by the derivative of y. That's going to give us y prime. Let's take a look at part D. In part D, this is a product. So the derivative of this is going to require the use of the product rule. It's the function x times the implicitly defined function y squared. The derivative of x with respect to x is 1 times y squared, plus from the product rule leave the x alone. Now we need to multiply by the derivative of y squared. Well, the derivative of y squared is going to be 2y times y prime. So our derivative altogether, just kind of cleaning up a little bit, we have y squared plus 2xy y prime. Some of the guidelines for differentiating implicitly is what we're going to do is we want to find the derivative, so we're looking for dy dx. So we're going to need to differentiate both sides of the equation with respect to the x variable. Okay. So we're going to take the derivative with respect to x of both sides of the equation. The next thing we're going to do after we apply that calculus step is we want to solve for dy dx. That involves getting all of the dy dx terms on one side and all of the non-dy dx terms on the other side. Once we've collected all of our dy dx terms on one side, we're then going to take and factor out the dy dx, and then we'll be able to simply solve for the dy dx by dividing by whatever factor is out in front of it. Let's take a look at example 2. In example 2, they ask us to find dy dx given that y cubed plus y squared minus 5y minus x squared is equal to negative 4. So first things first, this is an implicitly defined function. We do not have the y by itself. We wouldn't, for this particular equation, actually be able to write it in explicit form. And even if we could, the derivative is actually going to be much, much easier to find in the implicit form we're about ready to discover. So we're going to take the derivative with respect to x of both sides. The left-hand side is a collection of individual terms, so we just differentiate term by term. The derivative of y cubed is going to be a 3y squared. And typically for problems of this type, I like to use the y prime notation. It's a little bit less to write, and it kind of keeps the workflow a little bit cleaner because you can write inline versus having to write a fraction dy dx. That's the derivative of the first term. The derivative of y squared is going to be 2y, again we have y prime, minus the derivative of 5y would be 5, but then we need to multiply by y prime. The derivative of negative x squared is just negative 2x. And on the right hand side, the derivative of negative 4, that's a constant, so it's going to have a derivative of 0. Okay. So far so good. We successfully moved all of our terms to, we successfully took the derivative. The next step is to get all of our y prime terms on one side. So I'm going to remove by adding 2x to both sides. We have 3y squared y prime plus 2y y prime minus 5y prime is equal to 2x. Now that we've done this, y prime is a common factor on that left-hand side, so we can factor it out. We get 3y squared plus 2y minus 5 equals to 2x. And now the very next step is we need to divide both sides by that factor in order to get the y prime by itself. So we're going to divide both sides by 3y squared plus 2y minus 5. Divide by 3y squared plus 2y minus 5. And there we have it. These cancel, and we have y prime, or if you want to, you can call it dy dx, is 2x divided by 3y squared plus 2y minus 5. Of particular interest, one of the things that we note is if you look at our final answer here, it too ends up being an implicitly defined function. We don't have y prime equal to just stuff that involves x. This final answer as an expression contains both x's and y's, which in many regards makes sense because if we started with an implicitly defined function and we differentiate, it kind of makes sense that the derivative itself will end up being an implicitly defined function. Let's take a look at example 3. We're asked for the slope of the tangent line to the graph of x squared plus 4y squared equals to 4 at the point radical 2 divided by negative 1 over the square root of 2. We know whenever we hear the slope of the graph or the slope of the tangent line, we know that that's synonymous with the derivative. So we want to find the derivative of this function. Now, in example 3, it is possible. So you certainly could get the y by itself. It's not a one-to-one function, so there would be two branches, but you could choose a particular branch that would contain this point, and you could find the derivative using our other rules by differentiating an explicitly defined function. However, that algebra is going to get a little bit sloppy, and it's going to involve taking derivatives of square roots with some stuff on the inside, whereas even though we can, it's much better to do our new implicit differentiation on this one. We start by taking the derivative with respect to x of both sides. On the left-hand side, the derivative of x squared is 2x. The derivative of 4y squared is going to be an 8y prime. And on the right-hand side, the derivative of a constant is 0. So we took the derivative. The next step is we want to get the y prime by itself. So I could subtract 2x from both sides. That produces 8y prime equals negative 2x. And then the last step is just divide both sides by 8y, divide both sides by 8y, and we find that y prime, i.e. dy dx, is equal to negative x over 4y, and that's after we simplify our coefficients. So we found our derivative. It's an implicitly defined function, and we want to find the slope at the point square root of 2, comma, negative 1 over the square root of 2. One thing that's going to make this a little bit different, so the slope here is going to be y prime evaluated at that point. Because the function is implicitly defined, we're going to have to plug in both the x value and the y value into our derivative. This is the negative of the x coordinate, which is the square root of 2. And in the denominator, we have 4 times the y coordinate, which is negative 1 over the square root of 2. The negative divided by negative will cancel, so that will become positive. We're going to have the square root of 2 divided by 4 over the square root of 2 in the denominator. Do a keep, change, flip. This is the same thing as the square root of 2 times the square root of 2 over 4, which is the square root of 4 over 4, which is going to be 2 over 4, or a slope of 1/2. So for the curve, or the function that's implicitly defined by this equation, its slope of its tangent line, i.e. the slope of the curve, at the point radical 2 comma negative 1 over radical 2, it would have a value of 1/2. Let's take a look at example 4. We're asked to determine the slope of the graph of 3 times the quantity x squared plus y squared squared equals to 100xy at the point 3 comma 1. Let's go ahead and do that. So first thing we need to do is start off by finding the derivative. Again, it's another implicitly defined function. Let's do the derivative with respect to x on both sides. On the left-hand side, this is going to be a composition of functions. The outermost function is the squaring function, so I'm going to bring the power down. 3 times 2 is 6. leave the inside part alone. This is going to be x squared plus y squared. This reduces to the power 1. But now from the chain rule, we need to multiply by the derivative of the inside. The derivative of the inside, well, the derivative of x squared is 2x, and the derivative of y squared is going to be a 2y prime. Okay. So that's the derivative of the left-hand side. If we look at the right-hand side, what we actually have is a product. And I'm going to envision this as the product of 100x times y. So we need to use the product rule. The derivative of 100x is 100. Multiply that by y. Plus, now let's leave the 100x alone. The derivative of y is 1. But from the chain rule, we need to multiply that by y prime. So that's our derivative. And let me just kind of erase this here. So this was just simply a coefficient of 1 that was up there. So we don't need to really write it. So now the goal is to get the y prime by itself. And we see that, okay, this term has a y prime with it. And right now we kind of have a y prime that's like locked into this grouping. Let's distribute to get this out. So I'm going to distribute this quantity into this parenthesis. 6 times 2x is going to give us a 12x x squared plus y squared, plus this will give us a 12y x squared plus y squared. I'll put the y prime at the end of it when we distribute it. And then this is equal to 100y plus 100x y prime. One of the things that I noticed, and we're going to do this immediately if you want to, is notice that all of these coefficients, the GCF is 4. So we can divide it by 4 to kind of make it a little bit more simple. This is going to be now 3x x squared plus y squared plus 3y x squared plus y squared y prime is equal to 25y plus 25x y prime. I wish I had some more room here. So this is 25y plus 25x y prime. Okay. The next step, I'm just going to kind of skip a little bit, but just a little bit of baby algebra. Let's suppose we want to move all of the y prime terms to the left-hand side. So that's going to leave us with this 3y. We have the x squared plus y squared y prime. I would have to bring that negative 25 x y prime to this side, and I'd have to take all of the other non-y primes to the other side. So I'd have that 25y, and then this term would go over to the other side as a negative. So that's going to be minus 3x times the quantity x squared plus y squared. Okay. And now the very next move, I'm going to do 2 steps in 1 here. But your next step would be to factor out this y prime. So I factor out the y prime, and then you'd be able to divide by the factor that would be in front of it. So as our final answer, we get y prime is 25y minus 3x times x squared plus y squared. And this would be divided by 3y x squared plus y squared minus 25x. So that is our derivative. Again, don't be off put by this. Again, most of this is just algebra. It's just a matter of trying to solve for y prime. So it took a little bit of steps. And then lastly, they said that they wanted the slope of the graph at the point 3, 1. Again, we know slope is synonymous with the derivative. So everywhere we see an x, we'll put 3. Everywhere we see a y, we will put a 1. So y prime is going to be equal to 25 times 1 will be 25, minus 3 times 3 is 9, x squared plus y squared, well, that's going to be 3 squared plus 1 squared. That's going to be 9 plus 1, which is 10. In the denominator, we're going to have 3 times 1, that's 3. X squared plus y squared we saw was 10. And now we have minus 25 times 3, that's going to be 75. Let's go ahead and work this out. We get y prime equals, in the numerator, 25 minus 90. That should give us a negative 65. In the denominator, we're going to have a 30 minus 75. That will give us a negative 45. And now we can kind of divide from here. First of all, negative divided by negative is a positive. If we divide them both by 5, top and bottom, we're going to get 13 over 9. So the slope of the curve that was implicitly defined at the point 3, 1, it would have a slope of 13 over 9. Let's take a look at example 5. In example 5, they say find dy dx for the equation the sine of y equals to x, and then find the largest interval of the form negative a less than y less than a, on which y is a differentiable function of x. So let's go ahead and do this. So we're going to begin by taking the derivative of both sides. So we're going to do d dx of the sine of y. If you take the derivative of the left-hand side, we also need to take the derivative of the right-hand side. Again, this is a composition. The outer function is sine. So we need to use a chain rule. Derivative of sine is cosine. Leave the y alone. And now from the chain rule, we need to multiply by the derivative of the inside. We know that the derivative with respect to x of y, that's going to be y prime. This is equal to the derivative of x with respect to x is just going to be 1. And now we can get the derivative by itself by simply dividing both sides by the cosine of y. Dividing both sides by the cosine of y. So we get that y prime is equal to 1 divided by the cosine of y. So this is our derivative. They also ask us for what is the largest interval of the form on which this derivative is defined. Well, in order for this derivative to be defined, we need for the cosine of y to not be equal to 0. For after all, if cosine of y is 0, then we would have something that's going to be undefined. And instead of calling it y, I don't want anybody to get confused with this. Just think of it as like the cosine of theta. So here's our unit circle. If you think about the various angles, where is the cosine 0? Well, if we start with the angle 0, we would rotate. The first time the cosine ends up being 0 is at this angle right here, which is pi over 2. The cosine of pi over 2 is 0. So we would need y to be less than pi over 2. And similarly, if we start rotating, because we want a negative angle, they say it has to be of the form negative a to a. So if you start rotating this way, again, it hits 0 at this angle. That's 0, negative 1. Cosine is the first coordinate, and that would be the angle negative pi over 2. So this derivative, y prime equals to 1 over cosine of y, is defined certainly on this interval of the form negative pi over 2 less than y less than pi over 2.